about my own work in this field, but actually, I'm mostly going to be just giving an overview of different approaches in the field. So a lot of the work that I'm going to be talking about is not my own. Um, so basically the talk structure is going to be, first I'm going to talk about what is optimization under uncertainty with side information. And then I'm going to talk about how do you solve optimization problems under uncertainty with side information. And so I'm not going to assume that everyone here has an optimization background. So I thought I'd start by talking more broadly about optimization under uncertainty. So really at its essence, optimization under uncertainty is trying to choose the best action when some elements of your problem are unknown. And so choosing the best action is optimization, and then the uncertainty is that not knowing some of the problem elements. So for some examples of applications, you might be some retailer, and if you're a retailer, you have to decide how much of each product you're going to buy, but you don't know in advance how much customers are going to buy. So you don't want to get stuck with extra inventory, but you also want to make sure you buy enough inventory so you don't run out. Another example is air traffic management. So if you're someone like the FAA, who schedules air traffic or organizes air traffic, you might ask, how should I schedule arrivals to some airport? But generally the capacity of the airport is actually unknown ahead of time because it can depend on things like weather. So if bad weather comes in, the capacity of the airport is going to be lower than if there's good weather the whole day. If you're a delivery company like FedEx or UPS or any others, you might have to route some vehicles to deliver packages to people. And so one question you might ask is, how should I route these vehicles? But a lot of times there can be uncertainty in travel times along roads because they can vary due to things like traffic conditions, weather conditions, maybe construction, things like that. And really, there's a lot of problems that we don't perfectly know all of the information to the problem, and we still want to try to choose the best action that we can given this uncertainty. And there's a really long history of research on these types of problems. There's, it's been going on a long time, and there's a very established body of research on optimization under uncertainty. So kind of a traditional problem in optimization under uncertainty might look something like this. Here we have an objective function f, which depends on both the action that we get to choose and also depends on some uncertain parameter z, which is going to be random and which we aren't going to see until after we choose our action. So we choose the action x, and then the random parameter z is observed, and then we basically collect the objective function f of x and z. And then our goal is going to be, and another component of the problem is the feasible region. So usually you have a set, here I've just represented by this calligraphic X. And so you're going to have a set of different actions that are allowed, and you have to choose an action from your set of feasible actions. So your goal is to choose a single feasible action that's going to minimize the expected value of your objective function, given the randomness in your uncertain parameter. Now, one significant complication is that typically the distribution of this unknown parameter is not known precisely. So for example, if you think back to maybe the vehicle routing example, you don't typically know exactly what the distribution of travel times along a road is. You can maybe model it, or you maybe have data about it, but typically speaking, you don't know exactly what that distribution is. So in a lot of the literature on these types of problems, you have an assumption that you have some training set, and this training set consists of some number of observations, usually independent, identically distributed observations of this unknown parameter. So in a vehicle routing example, that would be like you have a whole bunch of observations where you've driven along this road and you recorded how long it took you to drive across that road. And using that training set, you can estimate your distribution of these uncertain parameters. And a very typical approach to then solving the problem would be something like sample average approximation, or SAA. And the idea here is just we approximate the expectation with a sample average. So on the left, we have the expectation. On the right, we've just plugged in each of our observations into our objective function, and we've taken the average. And so instead of trying to solve this expectation where we don't actually know the distribution of Z, we solve this sample average based on the observations that we do have. Now, these problems are not necessarily, I'd say, easy problems. One of the big difficulties in these problems is that the size of the problem tends to grow with the size of the training set. So if you have a very large training set, you can have really large problems. However, this type of approach has been really well studied, and in a lot of cases, if you put restrictions on the feasible region and the objective function, you end up with something that has a lot of structure that you can exploit. And so we have effective solution techniques in a lot of practical instances for problems like this, even though they may be very large. And this is just one approach that I'm showing here. There are a lot of other ways to approach these types of problems. A couple of popular areas are data-driven robust optimization and distributionally robust optimization. And these tend to make similar assumptions in that you have this independent, identically distributed training set, but then the solution approaches are a bit different. So there are other approaches out there. I'm just using this one approach as a typical approach, and it is a very popular approach too. But in practice, there's a complication, which is that a lot of times you don't just have your uncertain parameter by itself. A lot of times you have kind of contextual information, or what we're going to call side information. And this information is correlated with the uncertain parameter. So it gives you some information about the distribution. So if you think back to the retail example, if you're trying to predict customer demand, you can maybe build a predictive model out of data based on, say, sales of similar products or competitors' prices, or potentially non-traditional data sources. Like now you can search social media posts and see how often the product has been mentioned. So in this case, the side information would be data such as sales of similar products or number of social media post mentions and things like that. And so this side information can help you get an idea of what the distribution of the demand is beyond just data on demand itself. And similarly, in air traffic management, you do have historical data on related to the capacity of the airport, but you also have additional data that you can use that will provide you more information. So if you're trying to plan air traffic management movements on a given day, you have the weather predictions for that day. You also might be aware of if there's any, say, runway construction happening on that day. And so based on that context, you have more information about the uncertain parameter that you can use to improve your decision. Same with vehicle routing. So again, your travel times can depend on things like traffic forecasts and weather forecasts. So if I have a traffic forecast or weather forecast for today, then I can potentially make better choices because it gives me information about the distribution of these travel times. So yeah, so we're assuming that there's some relevant side information. And we're also assuming that we get to see this side information before the action is taken, because otherwise it's not very helpful. So these types of problems are going to require both statistics or machine learning or data analysis types of techniques, and also optimization. You need the statistics and machine learning to understand the relationship between your side information and your uncertain perimeter. And then once you have some knowledge of that relationship, you're still going to need optimization to choose the best action. And so if we come up with a formulation of a problem with side information, it might look something like this. So this is our same optimization under uncertainty setup. The only thing is that instead of taking just a plain expectation, we have a conditional expectation where it's the expectation of our objective function given an observation of the side information. So this variable y here is going to be the side information, and it's going to be correlated with the uncertain parameter. And so now we're going to allow our action to depend on the side information. So the whole point of this is that if we have some context, we can use that context to make better decisions. So our actions are going to depend on the side information. And so that also means that instead of just choosing a single action, we are going to look for a policy. And so this policy is going to be a function that maps the side information y into the action x. So if you give me side information, the policy is going to tell you what is the best action for the given side information. And so now our goal is overall is going to be to try to choose the policy that minimizes the expected objective, where the expectation is taken over both side information and uncertain perimeter. So it looks something like this. We still have our objective function, and instead of just choosing a single action, what we're plugging in here is the choice in the policy. So this pi of y is the action taken by the policy, and then z is our uncertain perimeter. So f of pi y and z gives us basically the objective under our policy. And then we take the expected value of that over over both the side information and the uncertain perimeter. And so we're going to look for the policy that does the best overall in terms of the expected value. And feel free to interrupt at any time if there's questions. Feel free to either just ask or throw them in chat. Yeah, but I'm going to keep going, but
sorry.
You go ahead.
Just a clarification about like when you write the problem in this formulation, which is on the screen, which means like you're considering your side information to be random now.
Yes.
Okay.
Yeah, so you could consider also trying to do something tailored to a specific side information, but in general, ultimately you want to come up with a policy that kind of stays valid over some period of time. And so you might get develop a policy, and then you get multiple observations of the side information, and you have to come up with actions to take in each of these observations of the side information. So for example, in like a retail application, I have to choose how much stuff I'm going to order today, but I also have to choose how much stuff I'm going to order tomorrow. And so those could be, you know, different instances of the problem with different side information. Or like a vehicle routing, I have to choose how I'm going to route my vehicles based on today's weather forecast, but I also have to choose how I'm going to route them in tomorrow's forecast. And so I'm going to look for a policy that stays valid for multiple, over some horizon where I can put in side information and get out actions.
I see. Thank you. Thank you for
Mm-hmm. Are there any other questions? Okay. So we're still going to assume that we have a training set, but now our training set is going to consist of pairs of values. So instead of just having n values, we're going to have n pairs of values, and each pair is going to consist of an observation of the side information and a corresponding observation of the uncertain parameter. So in a vehicle routing example, this could be like your side information is the weather forecast was such and such, and the uncertain parameter is like my travel time across these roads was, these values. So we're going to assume that each observation of the side information is correlated with the corresponding uncertain parameter value, but we're going to still have a training set that's overall IID, in the sense that if we treat each pair as a single observation, the joint distribution is going to be the same for every pair. And each of these pairs is going to be independent from all of the other pairs. To be fair, this assumption probably isn't exactly met in all of the applications that I've mentioned. For example, in a retail application, maybe demand tomorrow is very highly correlated with demand today. But we're just going to make this assumption. It's fairly necessary for a lot of theory to work. And there are potentially things you can do to make it work in practice, even if it doesn't hold precisely. So in the literature on this type of problem is pretty new. The earliest work that I'm aware of that talks about this type of problem was in 2010. And prior to about 3 years ago, literature was very sparse. And yeah, there's probably been more written on this problem in the past year than there were in all preceding years. But actually, this type of problem is not really new, in the sense that there's a lot of problems out there that have side information, and that companies or people in practice solve. So the question is, what were people doing before this literature came out? And there's two approaches that you can take before that don't really address the problem directly, but if you run into a problem with side information. So one thing you could do is you could ignore the side information. And another thing you can do is something called predict, then optimize. So ignoring side information has basically one advantage, which is that it's easy. All you do is you just throw out your side information, and then you just treat your problem like a traditional optimization problem under uncertainty. And you can apply sample average approximation, or you can apply any number of approaches from the literature. Of course, it has a big disadvantage, which is that you're not using the side information. So if your side information is actually relevant to the problem, that's severely suboptimal compared to using the side information, because the side information can improve your decisions. But this is one thing that people have done. Another thing that people have done is something called predict, then optimize. And predict, then optimize is, I think, a pretty good name for what it is. So what you do in predict, then optimize is you fit a regression model between the side information and the, 1 second, sorry. Yeah, so you fit a regression model between your side information and your uncertain parameter. And so what I mean by regression model is that's going to be basically something that takes your side information and it just returns a point prediction of your uncertain parameter. So for like a retail application, it takes in your features. So maybe like your sales of similar products, and it returns just a single point. I think you're going to sell 10 units of product based on this side information. And so you can use standard regression techniques here. You can use linear regression or time series regression, I guess, if it's a time series, or you can use lasso or any of the more modern machine learning techniques too, like random forests or support vector machines or neural networks. Like any of these standard regression techniques are fine because you're just doing regression. And basically you're just using your side information. You're treating those as your feature vectors in regression, and you're treating your uncertain parameter as your outcome in regression. And that's what you do. And so now you have a regression model that gives you a point prediction for each value of your side information. So we're going to use the notation phi to be my regression model. And so phi of y is a point prediction for my uncertain parameter. And then I just plug that into my optimization model and I solve. So basically, and that's all this equation here is showing on the right-hand side. I've just taken my optimization problem, I've removed the expectation, and I've just replaced my uncertain parameter by this prediction. And yeah, so you solve that problem and you just do whatever action comes out of that. So
can I ask you a quick question? So phi cannot be a distribution. It will be a particular C within the set.
Yeah, so phi is not a distribution. It's a single point prediction.
Okay, perfect.
Are there any other questions?
So if you since y is like a random variable, right?
Mm-hmm.
And so if you want to like minimize the expectations, you need to also take like the expectation respect to y, right?
Yes. So I should say, in this case, we kind of, our policy in this case is going to be to solve this subproblem with this point prediction. So kind of in optimization with side information, you have what you could call the overall problem where the side information is random, but you also kind of have subproblems for each fixed side information. So our approach here is that we're not going to explicitly build a policy. Our policy is we're going to build a regression model. And our policy is going to be, I'm going to solve this subproblem for each side information. So when I get my side information, my policy says, take your prediction from your regression model, plug it into this optimization subproblem, solve that subproblem.
Yes, thanks.
Mm-hmm. Any other questions?
Yeah, hi, Alex. Sorry, I joined late. So I have a question regarding the expectation. So the expectation here is regarding the prediction error, or
the expectation. So the expectation here is over the uncertain parameter. So we have the side information and we have the uncertain parameter here. So in this particular expectation, we've conditioned out the side information already, and we're just taking the expectation under the uncertain parameter. So Yeah, so for example, in a, say, vehicle routing example where your site information is maybe a weather forecast, then this expectation here would be the expected cost of your vehicle routing given the site information, the weather conditions.
I see. But so like on the other hand, on the right-hand side of this equation, so you get rid of expectation, meaning that you rely on your prediction, right?
Right. So I'm not sure how late you came, but you might have missed. Basically, what I'm talking about now are methods that people used before there was literature on optimization with side information problems. So this is maybe not exactly the best approach, but what I'm going to talk about in the next slide is when it's a good approach and when it's a bad approach.
Okay, thank you.
Mm-hmm.
And this is completely eliminating the randomness of this. This is getting rid of the distribution information kind of, right? So we're fitting like this phi of y, and then we're assuming that's it. We're just going to do a deterministic optimization. Would you ever fit like some of the parameters and leave some in? Like if you just have too many factors, would you ever just eliminate some of them or try to do something to reduce the number of factors with this?
Yeah, so something that people also might do, and again, there are more sophisticated approaches. I'm kind of leading into the more sophisticated, better approaches by talking about the approaches that people used to do before we had these better approaches. But even if you didn't have the sophisticated approaches, you could do something similar to what you mentioned, where you kind of combine these two not sophisticated approaches, and maybe you do predict and optimize on half of the parameters, but some of the parameters maybe you think are not so tied to the site information and have a lot of variance. And so you could leave those, and you could do like a combination of sample average approximation, ignoring the site information for some of the parameters, and then using a point prediction for the others.
Yeah, or just do something to reduce the number of factors to get like the site information to be like a smaller thing, and then do something like distributionally robust optimization on it, right?
Yes, you could do something like that too. Yeah. Okay, so any other questions? Okay, so this is sort of a naive approach, as you've rightfully caught on. This is getting rid of the randomness in the problem. It's replacing a distribution by just a point. So we don't expect it to work well all the time, but when does it work well? Well, most of the standard regression models out there, or the commonly used ones, are trying to estimate conditional expected values. So this phi of y you can think of as it's approximately the expected value of your uncertain parameter given your side information. So assuming that your regression model worked the way you wanted it to, what you now have is approximately your objective function of whatever action you're taking with this conditional expectation plugged in for the side information. So we expect this to work well when this conditional expectation of the objective function is approximately equal to the function applied to the conditional expectation. In other words, when we can take this expectation within the function, and that basically happens for linear functions. So we expect predict then optimize to work well when the objective function is linear in the uncertain parameter. So if it takes this form, then you'll find that that happens, and then it'll work well. So even though this approach is a bit naive, it does work for at least one class of problems, but it is somewhat limited. This is about it. So if your objective function looks like this, oh, and I should also point out that No, actually, yeah, it's fine. Just when the objective function is linear, is when it works well. But if the objective function is not linear, then it's not going to work well. So the advantages of this are, again, that we don't need any of this new literature that's come out. We can use existing techniques. And actually, this has one advantage over sample average approximation, which is that your optimization problems are smaller and simpler, because rather than using every data point in your training set, you're just using a single point prediction. It does, I guess, have another disadvantage other than the one I've mentioned, which is that you've completely removed all randomness. But a big disadvantage is that you're still going to be suboptimal, except for this pretty small class of problems. So what are we doing now? What does the literature say now? So there's basically three approaches that I've seen. One is conditional density estimation, then optimize. And the other two are based on empirical risk minimization. And I'll go through these one at a time. So the idea behind conditional density estimation, then optimize, is pretty similar to predict, then optimize. But here, instead of doing a point prediction, we're going to try to estimate the entire conditional density. So if we let this P given Y be the conditional PDF of our uncertain parameter, given that the side information took the value Y, then this conditional expectation takes this form of this integral. I mean, that's basically the definition of the conditional PDF. And I mean, it could also be a PMF. So if the uncertain parameter was discrete, it would be a PMF instead of a PDF. But I mean, it's basically the same. It's just a sum instead of an integral. So if we build an estimate of our conditional density for a value of the side information, then you can write these expectations as functions that you know. So if your estimate is continuous, you end up with this integral. If your estimate is discrete, you end up with this sum. For most of the methods that people use, they end up with a discrete conditional density estimate. Even if the parameter itself is continuous, the estimate will be discrete, because a lot of times it's supported just on elements of the training set, but it doesn't have to be. And there are some approaches where you'd get a continuous one out. For use in optimization with side information, the ones that produce a discrete estimate are more popular. And the reason for that is that this integral, trying to optimize over it, is pretty tricky. But this sum is actually, it actually ends up looking a lot like sample average approximation. So if we look at this sum, if our conditional density estimate is discrete, then the optimization problem we end up with looks a lot like sample average approximation, except that we're using a weighted average instead of an unweighted average. So instead of everything in the training set being weighted equally, the elements of the training set get weighted by probabilities. And so what you find is that even though it's not exactly sample average approximation, in fact, most of the optimization techniques for sample average approximation, they don't really rely on those weights being equal. And so they still work here. And again, you're doing a similar thing to predict than optimize, where your policy is going to be based on, I solve an optimization problem every time to get my action. So a lot of times you just fit one density estimate. Actually, a lot of times you just go for actually a joint density estimate. And then when you get an observation of the side information, you kind of translate that joint density, then you can get the conditional density from that. And that gives you this optimization problem, and you solve that to get your action. And so your policy is basically the one that's implied by this optimization subproblem, if that makes sense. Yeah. So the advantages of this are that it leverages existing statistical methods, because there are existing statistical methods for conditional density estimation. Some popular ones include kernel density estimation and random form-based or tree-based density estimation. So, and as I've already mentioned, the resulting optimization problems that you need to use to get your actual policy, those are ones that look a lot like sample average approximation and that we can solve. And a big advantage of this approach is this method actually converges to an optimal solution. And it's not too hard to prove this. If your objective function is sufficiently regular and your feasible region is sufficiently regular, then it kind of follows from results on your conditional density estimator. If that density estimate converges to the true density, then you're kind of solving the true optimization problem. And so you get the optimal policy. One of the disadvantages of this is that conditional density estimation can be quite data intensive, because you have to estimate a whole distribution, and it can be hard to get accurate estimations, especially of tail densities, without a lot of data. And we might be doing more work than we really need to be doing here, because for a lot of problems, we might not need the entire conditional PDF. We might just need certain elements of key information. So for example, kind of a classic result in news vendor problems is that the optimal solution is a single quantile that depends on the cost of buying and selling a newspaper. And so if you're looking at one of those problems, really all you needed to do was estimate a single quantile. But in this approach, you estimated an entire density. So those are advantages and disadvantages of this approach. Are there questions on this? Okay. So the next approach that people have looked at is, I'm calling it empirical risk minimization for learning a policy. And empirical risk minimization here, that's a very broad kind of strategy used in statistics. And so what I'm talking about here is kind of a specific application of empirical risk minimization. So the idea here is that we're going to restrict our attention to policies in some class, call it capital Phi. And this class of policies is usually something like you would use in a machine learning or regression model. So like linear models or neural nets or trees or random forests. So basically what we're saying is we're only going to look at policies that are, say, built from random forests. And so just to recall, given your side information y, if you have a policy phi, is going to take the action phi of y. And again, our goal overall is to find the policy with this best expected performance over both the side information and the uncertain parameter. So this is just plugging our policy in here. So overall, what we're looking for is the policy that within this class capital Phi that minimizes this expected value, where I've just plugged in the basically the action that the policy takes. Well, actually, this is just the same expectation that I showed you before. Yeah. So then we do something that is very similar to sample average approximation. So we're just going to approximate this expectation with its average over the training set. And we call that the empirical risk. And the difference between this and sample average approximation here is that we're using the training set that includes both the side information and the uncertain parameter here. But otherwise, it looks very similar. We're just taking the average of this over our training set. However, this problem actually can't usually be solved by a lot of the traditional literature on stochastic, or not stochastic, sample average approximation. And the reason why you can't use a lot of the traditional sample average approximation techniques is because these usually have requirements such as convexity of both the feasible region and of the objective. However, if you look at what's happening here, when we're kind of taking a composition of our policy and the objective function, and a lot of times when we do that, it breaks the convexity. So even if our objective function is convex, and even if our policy class is kind of nice and convex, a lot of times this composition is going to be non-convex. And so what you'll see here, the methods that go this route tend to look more like machine learning methods than they look like traditional optimization methods, where you kind of try to, you don't always try to solve this optimization problem exactly. Maybe you just do gradient descent and you stop at a local minimum or something. So maybe you have a neural net and you do gradient descent and stop at a local minimum. So the advantages of this approach is, well, to some extent, it's a standard regression problem. And to some extent, you can use regression techniques or machine learning techniques. This is a little bit not true because the objective here is not least squares. So a lot of regression techniques have focused on least squares, but there are also a lot of regression techniques that aren't necessarily specific to least squares. So a lot of existing regression techniques can work here, although some of them might need some modifications. You can also get some convergence guarantees out of this. Since you're only looking at a class of policies, you can only guarantee that you're going to converge to the best in the class, but you can guarantee that. And if you structure the class correctly, you can have guarantees where you like kind of expand the class as you get new samples. And you can, if you do that, you can get convergence just overall in general. So this does lead to an optimal policy, or at least it can. And an advantage here is that we're actually fitting our policy directly. So unlike the other two, or the other approaches that we've talked about so far, our policy is actually explicitly defined and we get actions directly for new side information. We don't have to solve a new optimization problem every time we get new side information. Some of the disadvantages are that it can be difficult to take advantage of problem structure. So in this approach, you might end up just treating it kind of like a black box regression problem, and then you can't use any problem structure. Another disadvantage is the optimal policy can be a quite complicated function of the side information. And so you might need some really complicated class of policies to get good performance. And then if you have a very complicated class of policies, that usually means you need a lot of data to train that class of policies. So for example, you might need to do something like deep neural nets, and then you need a ton of data. So this might not be super data efficient if the optimal policy ends up being a very complicated function of the side information. On the other hand, if you are able to exploit problem structure, this approach can be quite good. So there's one example in the literature where it's a very specific problem. It's a type of news vendor problem where you can show that the optimal action is just a quantile of customer demand. So then really your optimal policy is just find the quantile of customer demand. And so you can just rewrite this as a problem of estimating a quantile. And then there are good methods for quantile estimation. Yeah, there's good empirical risk minimization methods for quantile estimation. And so you can get that to work pretty well. But it seems difficult to apply more generally because, I mean, in this case, you have a closed form for your optimal solution based on your side information and a quantile of your customer demand. So in most cases, you don't have that closed form. And so it's kind of difficult to use your problem structure. And so in a lot of cases, you'll end up going with more of a black box approach, and then you'll have the disadvantages that I mentioned before. So questions on this?
So the phi function here is like a mapping from your side information to the action, right?
Yeah, that's correct.
Yeah, I'm just thinking of like, because your phi belongs to a set, right? This capital phi. So do you like have any information about how you typically construct such a set for the phi function?
I mean, it's going to be similar things to what people do for machine learning. So as I mentioned, this type of approach tends to draw more from machine learning than optimization. So usually it'll be like people are really good, you know, it's like if you're a neural net expert, your class is neural nets. If you want something that kind of works well and that's not as difficult to train, you might try random forests, those kinds of considerations.
I see. But so for this problem, we do not require the object function f is a linear function of the uncertain parameter, right?
Yeah. So in this case, this you can get convergent results for a very broad set of objective functions. And much broader. You don't have to assume that it's a linear function.
I see. So that linear function restriction is only for the conditional probability method, right?
Yeah, so that's only for the that predict then optimize method.
Okay, I see.
Yeah.
Thanks.
And actually another disadvantage that I didn't list here is that this can be very difficult to work if you have complicated feasibility constraints, because your policy, like if you fit a neural net, it's actually kind of difficult to make a neural net that always produces a feasible action. So this approach can also be difficult if you have complicated feasibility, a complicated feasible region. So are there any other questions on this? Okay, so the last approach that people have looked at is called, I'll call predict and optimize revisited. And this is something that I've worked on. So this is very similar to predict and optimize in the sense that we're going to build a regression model and we're just going to get a point prediction from it. And we're just going to plug that point prediction into the optimization problem. However, instead of using standard regression techniques, we're going to use empirical risk minimization principles to get a better procedure for fitting this regression model. So suppose that we had some observation of our side information, y. So then if we have a regression model phi, our point prediction for the uncertain perimeter would be phi of y. So if we were following predict then optimize, what we would do is we would solve the optimization problem, take the min over our feasible region of this function with the point prediction plugged in. And so that'll give us some x star that is an argmin of this optimization problem. And so then if our uncertain parameter turns out to be z, the objective value that we're going to actually achieve is going to be f of x star and z. And then if we look at how we define x star, we get this kind of nested looking thing where we have the function applied to this argmin of the function. So if we were using predict and optimize, this is the objective value that we would achieve. And so what we're going to do is we're going to try to find the best regression model to minimize this actual achieved objective value. So it's going to look something like this. So we take the minimum over a class of possible regression models. Again, you can use whatever class you want here. You can use linear models, neural nets, random forests, anything you want. And we minimize this expected value taken over both our side information and uncertain parameter of the actual objective that we achieve with the predict and optimize approach. So I'm going to now change the name to objective aligned regression just to avoid confusion with the naive predict and optimize approach. So objective aligned regression is going to refer to this improved predict and optimize. And again, what we're going to do is we're going to replace this expected value here by taking a sample average. So this expression here is then our average over the training set. We've just plugged in the side information and the uncertain parameter. And then usually we also normalize by subtracting off the best possible objective value. That doesn't actually change the fitting problem because what we're subtracting here is a constant. So C star of Zi is the best objective value that we could have achieved if we knew that the uncertain parameter was going to be Zi. But what that does is it makes it so that this value here is always positive, or at least non-negative, and it takes a value of 0 when your prediction matches with the uncertain parameter. Something else to notice is that this is actually not 100% well-defined if argmin is not unique. And so if there's multiple optimal solutions to this inner optimization problem, you have to choose exactly how you're going to choose between those optimizations. And actually that can affect both what this fitting problem looks like and how tractable it is. So some advantages of this is that you can use a simpler class of models than if you were trying to learn the policy directly. So this, because you're still just trying to learn the relationship between the side information and the uncertain parameter, rather than trying to also, kind of capture the optimization elements in the fitting problem. Another advantage is you don't have to learn the entire conditional density. You just have to learn one point prediction. So in theory, or at least intuitively, that could make it more data efficient than CDE than optimize, or by the empirical risk minimization for learning the policy. However, that's really, at this point, that's not proven yet. And it's still an open question whether that's true in practice. But at least intuitively, you would think that maybe there are some data gains there. Another advantage over CDE than optimize is that the optimization problems that you get out of this are simpler because you're just using a point prediction instead of using like the entire training set when you're choosing an action for fixed side information. So one of the big disadvantages of this is that the fitting problem is very difficult. So this, I mean, if you look at it, it's quite complicated with this argmin inside of this function, and then this minimization out there. So it's kind of like a bi-level optimization problem that's quite complicated. And so existing optimization techniques and existing statistics or machine learning techniques don't always work well for this fitting problem. We need new techniques for solving these fitting problems. In fact, this fitting problem so far seems to be, I'd say, intractable in a lot of cases. So you have to approximate it. You won't solve it exactly. And another downside is that at this point, it's kind of unknown whether it converges to an optimal solution. I mean, one of the things here is that we're still replacing a distribution with a single point. We're doing it in a more principled way than we were doing before. And I can give you examples where the costs are not linear in the uncertain parameter, and this does converge to an optimal solution. But I can only give you specific examples at this point. I can't tell you in general, you know, under these conditions, this is valid, and under these conditions, this is not valid. And this is especially complicated when you consider the fact that we often can't solve the fitting problem exactly. So there are cases where you might be able to say, if we could solve the fitting problem exactly, we'd be able to get a convergence to an optimal policy. But if you're using an approximate method, then it's unclear. So those are the downsides. Is it okay if I go a couple minutes over here? I know we've reached 5 o'clock.
I think that'd be fine.
Okay. So in my work, I've looked at objective aligned regression for a type of problem that's a two-stage linear program. So if you're familiar with, if you've seen two-stage stochastic programming, this problem probably looks very familiar to you. If not, then don't worry about it too much, but this is a pretty common optimization problem that has a lot of applications. So if we look at this fitting problem again, basically, in order to optimize this fitting problem, we really have to understand what's called the risk function. And so the risk function takes your prediction and it takes the actual value, and it gives you, really, it gives you the regret that you have if you use your prediction, z hat, when the actual value is z. So this expression here is like the difference between what you achieve if you have the prediction z hat versus the best value that you could have done if you had known the true value. So this fitting problem is really just minimized over this policies, the average of this risk function with the prediction from your model plugged into the risk function. And one of the big difficulties of this is that the risk function in objective aligned regression is typically very often non-convex. And so here's an actual example from a relatively simple one-dimensional problem. So the non-convexity here happens towards the end where it flattens off into just a straight plane that goes off to infinity. And so if you have a non-convex function, there are kind of standard ways of replacing it with a convex function. And one of those standard ways is to do what's called a lower convex envelope, which is basically the largest function that's still an underestimate of your function that's convex. Anyway, the point is, in this case, actually taking this standard approach doesn't work, because what you end up with is something like this, where basically you're accurate for the first part of the function, but then once you reach 0, you just stay at 0 forever. And that's a problem because what that actually means is that your estimate tells you if I overestimate demand, my regret is 0. But that's wrong. There is regret there, and it's just not calculating it. So we built a different approximation that in this case would look something like this. And I'm not going to go through the details, but basically, we very carefully build this approximation in a way that avoids introducing all of those new minima, those that the lower convex envelope introduces. And to be clear, our method works for any of these two-stage linear programs, not just this one-dimensional simple example. And we have some guarantees about our approximation. It's convex. It's always an overestimate of the risk. Or, I mean, it doesn't always overestimate, but it never underestimates, and it can overestimate. So you don't have those situations where you think you're doing a lot better than you are, but it can be suboptimal because of the overestimation. And then we can fit linear regression models by solving a linear program with this. We do have to use some techniques from optimization. So we have to use cut generation, if you are familiar with that, because our linear program has a lot of constraints, exponential number of constraints. But using some techniques from optimization, we can get it to work. So basically, the takeaway that I want you to get from this is that optimization with side information is, I think, a pretty important problem, actually, that comes out a lot in practice, but it's one we don't really fully understand yet. And there's a lot of potential here in terms of improving our knowledge in this area and making better methods that are more data efficient and computationally efficient. So that's it. And if there's any more questions, I'd be happy to take them.
I think we'll move on to the question answer session then. Does anyone have any questions?
Thanks for the presentation. I just had one question. So, can you hear me?
Yeah, I can hear you. What's your question?
Thank you. Yeah. So yeah, I just wanted to ask, like, so in your approach, you're still trying to improve the predictor for your uncertain parameter, right?
Yes. So in particular, what we're trying to do is, instead of making it a predictor of the conditional expectation, we're making it a predictor of something else. And it's a little bit unclear exactly what that else is, to be honest. But what we're trying to predict now is something like a single point that captures all of the distributional information that we need. So I can give you an example that might help frame this. If you're looking at something like the news vendor problem, where it's known that the optimal policy is a quantile, if you apply this approach, it actually ends up looking like quantile regression. So in that case, our point prediction is actually the point prediction of the quantile. So in that case, what we've done is we've produced the point prediction, but actually it's the point prediction that we need that kind of forces us to choose an optimal action. Now, it's not clear in general that this is going to work in every problem. Like, it's not even clear that such a thing exists in every problem. So to be honest, this approach is maybe a little bit fundamentally shaky at the moment. But yeah, does that make sense? Does that answer your question?
Oh, okay. Actually, I'm kind of like thinking what. So I'm still thinking like, what's the phi here now? Yeah. I think else people others can ask the question.
Yeah, it's actually a complicated question in this question, like what exactly is the phi doing? It's not clear for a general optimization problem, but the intuition is something like the phi is trying to pick a point prediction that makes you get the right optimal value for the distribution. It's trying to capture an entire distribution in a point somehow. Yeah, any other questions?
So does phi implicitly capture some of the correlation within Y and Z, but it feels like it only captures the one it needs for a particular point?
Yeah, so it's trying to capture some distributional information and represent it in a single point.
Right.
But again, it's not clear that this actually works. Like it's not clear that you can actually compress a distribution to a single point. That's one of the big open questions about this approach.
So, adding to that question, so like when you are considering this argument thing, so it is basically you're considering phi of y as an estimator for zi, or like what? So what is the role of phi of yi when you're doing this argument thing?
Yeah, so when you do the argmin, you are treating the phi of yi as a point estimate of zi. So another way of thinking about this is you're kind of trying to trick, predict, and optimize. So predict and optimize thinks it has a perfectly accurate estimate of the uncertain parameter. And so instead of feeding it a perfectly accurate estimate of your uncertain parameter, you feed it something else that you think will make it choose the right action given what you know about the distribution.
Okay.
So like in a news vendor example, actually like the optimal, if you know the demand exactly, the optimal action is just to choose the exact demand, right? But if you know a distribution, the optimal thing is to choose a quantile of that distribution. So in that case, what predict and optimize does is instead of feeding it its like best prediction of what it thinks average demand is going to be, it feeds it that quantile. And then the optimization problem says, okay, if I assume that the demand is this quantile, I should just choose my action to be, this value. And so you're sort of tricking the inner optimization problem into choosing the right action, even though it thinks it has perfect information. That's the goal.
Kind of a follow on this. So when you kind of ask it to do the fitting with like some sort of information that you, I guess, like given whatever the yi's are, if you now observe like a new yi that's not in your data set, do you have to add it in and then redo the fitting? Or maybe I'm just confused about how that.
So that's a little bit application dependent, but typically what you would do in something like this is you would have kind of do it in batches. So you collect a bunch of information on yi's and zi's. You use that to fit the model. And then you kind of have a policy that you can run for a while. And then while you're running this policy, you collect more yi's and zi's. And then every once in a while you refit your model. So like if you're doing an air traffic management example, you get like a weather prediction each day, and then you get actual observations of capacity. At the end of the day, you can look back and see, okay, what did my capacity actually look like? And so I'll fit a model based on that, and then I might run the model for like 3 months. And then after running the model for 3 months, I have like 90 more observations. And so then I can fit the model again, and then I can run it again. But you don't need to fit it just because you have something else. Yeah, so another thing is that that might have been in your question is that you don't necessarily have to refit every time you get a value that you haven't seen before, because I mean, regression models kind of interpolate between values that they haven't seen before. So they can still produce predictions even if you haven't seen the value before. As long as you have some observations that are somewhat similar, you can probably get an accurate prediction for that value.
Okay. I see. Yeah. So like if you see something that's like just really extreme, then maybe you'd want to rerun it. But if you kind of think that'll fit for some time frame, then you can just kind of update it as you go.
Yeah, pretty much. I mean, if you see a value that's extreme, then a data-driven approach is not always the best approach in general. So these data-driven approaches all kind of assume that you have at least enough data that if something that you can make accurate predictions for kind of anything that comes up. But you probably, if you're implementing this in a real system, you probably do want to have something where you're catching extreme examples. You say, oh, this is way outside of anything I've seen in my training set. And then maybe you have a human in the loop, or you have something that can deal with that extreme observation. And then maybe over a very long period of time, you might collect enough observations that that observation that previously looked extreme no longer looks extreme, because you filled out your observation space. But until then, if you don't have enough data, you do want something that catches that and says, I don't have enough data, I need a person or something to make this decision.
Oh, okay, cool. Thank you.
Just to repeat, like, so as you already said, like this approach would work well, like if you can like suppress a distribution to a point, right? So also I just wanted to ask, like, is there any like iterative approaches you can just apply to solve this problem? Because you're doing just two type like minimization. So.
You mean the iterative approach in terms of solving the fitting problem, or solving the overall optimization
solving the overall
problem?
Like overall problem.
It depends what you call an iterative approach. I mean,
so yeah, okay, sure.
Yeah. Can you kind of
so kind of I was thinking like so it seems like you're first minimizing by treating your predictor to be a right estimator for your uncertain parameter, and then you try to minimize that fitting for that uncertain like for your phi basically. So can you just like first randomly, just like in neural nets, or like you would just randomly do initialize your parameters for your phi, and then iteratively update them by choosing between like how's the prediction?
Sure. So I think what you're suggesting is kind of like it's kind of like the ERM just building a policy directly approach, if I understand you correctly. Or are you still suggesting doing this in the like improved predict and optimize framework? But I mean, you can definitely do a policy and then just do like gradient descent on your training set with the policy with your deep neural net, and you'll get something. I mean, I guess you can do something similar in the predict and optimize approach too. So you could like make your class of policies here neural nets. And then you could solve this fitting problem kind of by doing gradient descent on the neural net. Potentially, you could also do an approximation for this argument. So you don't necessarily have to solve this argument exactly in your problem. So like, yeah, potentially you could do a kind of double iterative approach where you kind of have a neural net or something that is trying to find the argument, and then you have another net outside that's trying to find the policy. I mean, there's lots of different things you could try. All of these. Yeah.
Actually, I was thinking on those lines only. Thank you so much.
Mhm.
I think if you have no more questions, thank you, Professor Estes, for giving this talk.
Yeah, thanks you all for coming.
Yeah.
I appreciated all the questions, and I hope you enjoyed the talk. Thanks for having me.
Thank you.
Thanks. Bye.
Bye.
Yeah, thank you.
Thank you. Thanks.